You looked at problem number 3. Problem number 3 is about circular motion. But we spent quite a bit of time looking at simple harmonic motion. And in dealing with simple harmonic motion, we know that the period of oscillation is related to two things: the length of the string and the acceleration of gravity. Now, we just finished taking a bunch of data. If you didn't get the actual data, I have it recorded on my watch here. It was for the simple harmonic motion part. So I'll put T SHM, we got 22.5 seconds. That was for 10 swings though, so that suggests a period of 2.25 seconds. But then we had the period that we measured twice for circular motion. I'll put uniform circular motion. What did we get for that? That's the last one I was on my watch. I have 23.35. Ooh, is it possible this was 23 and not 22? I think it was, you're right. And there Mr. Shelton goes, spouting lies. There we go. So that suggests, of course, that the period, that's for 10, suggests that the period was 2.34 seconds. Now, I can't say that they're the same. I can say that they are very close. Wouldn't you guys agree to that? And they measured really close. So what I'd like to do is twofold. First, I'd like to experimentally demonstrate that we were very close in our measurement. But we should also theoretically show that we're very close. Now, you guys know where this came from, or at least we talked about where that came from. We know that it involved us looking at the forces acting on an object, returning at the center. We know that we had to make some, what's the right word here? We had to fudge it a little bit for the fact that an object in a pendulum travels along a curved course to get to the center. Do you remember that? We talked about the difference between this and this path. And then we might not have done this in every class, but I think we tried to compare the fact that what it really came down to is comparing theta with sine theta and showing that they, for small angles, were close. What I'd like you to take a moment and do is, what is our theoretically predicted period? You know the length. We should use gravity as 9.8, not 10, and take a moment and calculate the theoretically predicted period. Now, while you do this, I'm going to wait patiently, but I'm expecting you to put that period in the chat window when you've received it. If you're having difficulty, you should let me know. Nordy's was first, Jesse Kim second, James Harris third. Look at all those. How'd you get 20? So we got 20. I think we're looking at 2.37. So I would say that we theory's lining up with prediction pretty close, huh? Now, what we really need here, there was no M. If we're trying to see if these things are similar, having the M cancel out, that's a good thing. That we expect to see when we're dealing with the period, and it looks like it's going to be the same. Consider is, well, how does this pertain to the situation that we were given in the problem on problem 3, where we have this object that's going to be in uniform circular motion. So it's clearly different, uniform circular motion. I'm going to try and draw this so that it kind of has that same look as the one on the homework. And we're kind of given this idea that there's an angle theta here, there's a length of string here, and our object is going about a path like this. Now, our job is to figure out what the period is here. But there's a couple of things that we have to do to get to that period. First, we know from discussing uniform circular motion that an object that is in uniform circular motion must have a centripetal force acting on it. Something has to cause this circular motion, so there must be some component of the force towards the center of the center of the circle. And we know that that unbalanced force is going to produce an acceleration that is proportional to the velocity and the radius. Now, the real question comes down to, how do we get to this and relate it to period? So in fifth period, I probably went about this the wrong direction. So in this class, I've decided to make a small change in the order in which we talk about this problem. Now, this is not problem number 3. I don't know what problem number 3 asks, specifically A, B, and C. I do know that we can discuss, from just looking at this, what the period must be in terms of measurable dynamics, like what the mass is that I hung, what the length of the cable is, what the angle is. These are measurable dynamics. We should be able to get the period from that because we know about uniform circular motion. And because of that, I should at least be able to use this relationship. But this relationship doesn't tell me period. It can give me things like velocity, but it can't tell me period, which requires a reminder that velocity is probably related to how far the pendulum bob travels, the distance of the circle, and how long it takes to do so. I mean, this is where the period is embedded. So I'm pretty sure that if I can find an expression for the centripetal force, I could use it to figure out the period. All right, does that make sense to all of you? We need to figure out the centripetal force. And here's where it's going to get a little tough, because I know that there are two forces acting in this system: tension and weight. And neither one of those point towards the center. But one of them, the tension, looks like it has at least a component that's aimed towards the center. So I'm thinking what we need to do is consider a coordinate system that's aligned towards the center of the circle. And that coordinate system would have, we'd have the y direction and the x direction. Now, in this coordinate system, I think we're also going to have to break this up into net force in the x direction and net force in the y direction. Net force in the y direction is pretty easy. It's 0. And it's the net force in the x direction that's going to give us our mv squared over r. Now let's think about the net force in the y direction for just a minute, though. The net force in the y direction has two components. There is the part of the tension that's acting upwards and the weight acting downwards. Now, this is going to be hard for some of you because this is really mathy, but I'm not scared of the math. So I want to, and this class generally isn't scared of the math. So I'm going to remind you that this angle is also theta. And I know that because I remember freshman year geometry, which I believe might have been my 8th grade year, but it's hard to remember. It's a long time ago. But there's that thing called alternate interior angles, of which theta is. That lets me know that this is actually going to be t cosine theta. So for this question, I have t cosine theta upwards and mg downwards, and they have to sum to be equal to 0. Thank you.
You're welcome.
My daughter just brought me jelly beans.
They're Starburst flavored.
Starburst flavored jelly beans.
Oh, why is it so sour?
They're sour jelly beans.
Wait, who eats these?
I forgot what the Easter Bunny brought. The Easter Bunny brought them sour jelly beans. I'm not a fan. These can go.
Well, did you only have the red ones, or did you eat a different one too?
I had a pink one. It was no good either.
Okay, we'll try blue one.
Back to work. So let that simmer for a few minutes. The t cosine theta equals mg. Set it to the side because what we're really interested in is what's going on the other direction, this way. Which you guys probably recognize, that's going to be the sine coordinate. So we're going to have t sine theta equals m v squared over r. Now, in case you're getting lost in all this because of all the crazy stuff, there was jelly beans here just a moment ago, and yes, I do miss candy corn. Remember, our goal here is to try and find an expression for the period in terms of things that we can measure. That's what we're trying to get. So right now, when I look at this, there's not a whole lot I can measure. I can measure the mass. Yep, I can measure the mass. I can measure r, but in our problem, they did not give me r. They did give me the length of the string and the angle, though. So the length of the string and the angle could be used to figure out r. I'm scared for some of you because I'm afraid some of you don't know that. But, I mean, I do see a triangle right here where r is a side and L is a side. So I'm just emphasizing it by drawing it a lot, but I'm just going to do that and it's all going to disappear. So can we all just, recognize it in a few minutes? There's probably going to be an r equals L sine theta later. I know, mathy math, lots of letters. I'm not scared of letters, so let's keep going. Let's see if we can't get rid of that t. Because let's be honest, the thing we don't want is t. We can't measure the tension. But I know that t is related to mg, so I can see that. And I think I'm going to do that first. So I'm going to say that t equals mg over cosine theta, and I'm going to make that substitution here. So that gives me mg times sine theta over cosine theta. And yeah, I know I could turn that into tangent. I'm not going to, because I'm going to be putting a sine theta in there eventually. I'm probably going to have to get rid of that tangent or something. I'm just going to leave it like it is for now. But this equals m v squared over r, and the first thing I hope you see is m cancels out. Now look, I kind of like the fact that m cancels out, because on the other hand, having sines and cosines, less of a good thing. But I'm ready to press on. Can we press on? All right, so I see a few people say yes. I'm going with the few people who say yes. I'm not listening to all the black boxes. There's a sea of black boxes here. I can't see any of you. So for all of you who are nothing but black boxes, phooey on you. For all of you who's beautiful, I guess maybe just the beautiful people. They have their cameras running. So hello, beautiful people. Glad all of you have your cameras running. It's good to see all of you. And it's good not to smell any of you. I made that joke in 5th period, and somebody was actually offended by it. You know who was offended? The smelly person. They're always offended. But they offend. So it's, I feel it's turnabout's fair play there. All right, so this screen is very cluttered. Would you agree it's very cluttered? I'm going to go to a new screen. That's what I had left. Yep, see? With less clutter. G sine theta over cosine theta equals, here we go. Remember, V is 2 pi r over the period. And over here I had v squared over r. Yep, there it is. So I'm thinking it's time to get rid of the v. Are you okay with us getting rid of the v? I'm okay with us getting rid of the v. And since I'm in charge of this boat, I'm going to put the v right there. 2 pi r over t, all quantity squared. This is the v. But I've just put in, 2 pi r over t. Now we should probably, do some more, wipe some math all over that again. G sine theta over cosine theta equals 4 pi squared r over t squared. This is looking like a mess. Yeah, we could. And I said that earlier. We could call it tangent, but And here's why I'm not going to, Matt. And I do think you brought it up. So R equals L sine theta, right? So I see this substitution occurring in a minute, and I had a feeling that there might be some shenanigans with the sine perhaps canceling out, so I didn't want to convert the sine over cosine to tangent. So I left it all very explicit so I could go back in here and now put this as L sine theta. I got a lot happening here, but one of the things that is happening is the sines are going to cancel out. Now we are nearing the end. I think you can see that we have to be nearing the end because we got our t in here. We got the period in here. And I got an L in here and I got a G in here. These are all those things. So let's keep wiping some math on it. I'm going to multiply both sides by t squared and divide both sides by g. So this is a lot for some of you to do this in one step, but I'm indifferent. And more importantly, it's 228. So t squared on one side and times 1 over cosine theta equals, and on the other side, I'm going to have 4 pi squared L over G. Looking good, huh? I mean, all that's left is to put the cosine over on the other side. And I'll get t equals 2 pi times the square root of, well, L over G cosine theta. What? Cosine theta, though? Really? It's so close to the pendulum one. So close. Of course, with the pendulum one, we had to do some fudging. Do you remember us doing some fudging? I mean, because it wasn't the actual arc. So we did some fudging. The fudging we did had to do with this. We just said that theta equaled sine theta, just waved our arms in the air. Why? Because we're in physics. We're not in math. Math doesn't let you wave your arms. But you know what? In math, a 79.99 is still a C. But in physics, it's not. It's a B. Now, you might wonder why that's relevant. I'm going to show you why that's relevant. 10 degrees. Would you say that's a big angle or a small angle? Remember, we said that this worked for small angles. So I'm thinking 10 degrees is small. Make sure your calculator is in degrees and figure out what the cosine of 10 degrees is. I know. Isn't it though? And then wait. Just because, I want to make sure that we're all understanding why I'm having you do this ridiculous thing. I'm going to separate them. Because take the square root of the cosine of 10 degrees. Yeah, that's what I was thinking. 0.99. Wouldn't you say that that's 1? You would if it was your grades. If it was a 79.99, you would say that that was an 80. I know. Perhaps not in like statistics or algebra 2. But in physics, that sucker is 1. Small angle theorem again. Small angle theorem is a real thing. We're going to use it. And this is why the period ends up being about the same. For a very similar purpose. That under these conditions, if the angle is small, we get a period of rotation that's very similar to the period of oscillation for a pendulum of the same size. Now, I know this was very heavy on the math today. And I can't say this was a whole lot of review, because it wasn't. This was a new, it's an interesting take on this problem. And why sometimes there are a lot of emphasis on the math? Because I think you guys can take it. And if you can't, I think it's a good experience for you guys to see it. Now, that brings us to the end of our discussion.